Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I want to thank all of you for joining us in our webinar today on July 24th, 2019. And I'm excited to talk about today's content with you all. We're going to be talking about relief valves. And actually, you're going to see all of our software tools today, AFT Fathom, AFT Arrow, and AFT Impulse, and how you can model relief valves in each of those different software tools. And they're all very similar, but each of the different products has their own different nuances. And so I'm going to touch on all of those products today. Where can you find more information about our software? Well, simply go to our website, aft.com, and then under the products menu, simply go to the AFT software overview. And this is where you can find more details about each of our software products, AFT Fathom, AFT Arrow, and AFT Impulse. And you can find a ton of information there. There's also tons of information under our Learning Center, like our case studies. Our technical papers is vast. We've added recently a few new technical papers up here that have been recently presented at multiple conferences, and lots of good reading material there that will help you learn more about analyzing piping systems and things that are important there. Another area to keep an eye on is our tips and tricks page. We're constantly putting out new blog articles that will show you how to use our software in more efficient and effective ways. And we've got hundreds of excellent blog articles here. Even blogs from 7 or 8 years ago are still pertinent today. So when you have some time, peruse through this list. You can find a lot of good information there. And many of these tips and tricks articles actually come from common technical support questions. So if there's something that you are having trouble with or something that you have a question on, chances are you're going to find a really good blog article in this list that will tell you how to get around what you're trying to do. So be sure to go through that list. Keyword searches are really helpful to find what you're looking for in that page. The next thing I want to talk about really quick is a newsworthy item, and that is our brand new automated network sizing module has been available for AFT Fathom for a couple of months now, and now it is brand new available with AFT Arrow. And so if you were to go to the downloads page under current versions and then go to download AFT Arrow, this is the latest release of AFT Arrow, and if you were to download it, that release and any releases later will contain the automated network sizing module. And if you have a license for it, then you'll be able to turn it on and activate it, and it will allow you to automatically size pipes in your system in order to automatically meet your design requirements while minimizing your overall piping weight, or even better, your actual piping cost for material, installation, maintenance, and energy. And so if you just go to our homepage, aft.com, under this banner right here where it says view details, well, you click on that and you can view more details. It'll ask you if you're an owner operator or an EPC firm. The message is just slightly different, but the software is the same. And so this will give you some more details on how the ANS module can specifically help you depending on if you're an owner operator versus an EPC firm. So be sure to check out this area. Very soon we'll have the AFT Arrow ANS page up, but it is available for you to purchase now. Last thing I want to talk about is notifications. If you go to the support menu under notifications, this is where you can be notified of all sorts of different things right in here. Our AFT newsletter, this is where we will publish a couple of tips and tricks articles each month that are really useful. It'll highlight a really good blog article that our president of AFT will write. We will document case studies and talk about other newsworthy items of things that are going on here at AFT. If we're attending trade shows or things like that, or we have training seminars coming up. So be sure to subscribe to our newsletter. It'll also alert you when we have new products available, like the new ANS module for AFT Arrow, and then other future products and new version releases down the road. Other things that are really important to pay attention to is our maintenance releases. Periodically, we will put out a maintenance release for our software that will address various issues and upgrade things and update things. And that way it'll help the software be a lot more efficient and effective for you. And so if you fill out the form and subscribe to any of those notifications, you will receive an email whenever we come out with a new maintenance release. That way you can have a link to go straight to our website in order to download the new maintenance release, or it'll give you a notification you can start bugging your IT department to go get the new release. So be sure to check those out. Incidentally, if you are in the software itself, you can determine really quickly if you're using the latest release or not. So if you're using AFT Fathom, you go to the help menu, just come down to AFT or about AFT Fathom, and this will tell you the release date. So if you look right here, this is the release date that you are currently using. If you write that down and then you go to our webpage where it says Internet latest release, that'll take you straight to the Fathom download page, and you can immediately identify if you're using the latest release or not. 8 times out of 10, simply updating to the latest release will fix whatever issue that you might be seeing when it comes to tech support questions. So be sure to make sure that you're staying up to date with the latest releases. Even if you don't have privileges to install the updates, you are still welcome to register with our website. Anyone is allowed to register, and that way you can at least download it and then give it to your IT department if they have to install it for you. All right, so let's go ahead and get into the fun stuff that we're going to be talking about today, which is AFT relief valve modeling capabilities. Before we jump into that, I did some research on relief valves, and I provided a couple of handouts for you. If you're listening into the live version of our webinar right now, those PDFs are available for you to read, and they are excellent technical papers on relief valves. The first one that you'll want to read is called What Pressure Relief Really Means. This is an article that was available in the American Institute of Chemical Engineers magazine in September 2010. And then there was another relief valve article that was written a few years later on sizing pressure relief devices. And this was published in October 2013. Both of those are excellent technical papers that will talk more about relief valves and just various things that you need to understand with how they work and whatnot. I really enjoyed them, and I've made them available to you. Incidentally, this webinar is being recorded, so if you're listening into the recorded version of the webinar, feel free to email me at benkeiser@aft.com. That's BENKEISER@aft.com, and ask me for the 2 technical papers on modeling or on relief valves, and I'll be happy to send those to you. So that will give you some good background information. One of the things that I learned when I was reading these articles here is that there are some very basic equations that you can use in order to calculate, the size of relief valves, your flow capacity, stuff like that. And so when you read through these technical papers, if the only thing that you care about is determining the relief flow rate and that's it, and you don't care about anything else, then our software might be a little bit of overkill compared to the equations that you can use right there in those technical papers. So why in the world would you need to use our software for relief valves? Because honestly, it's not one of the most exciting things to model. Your relief valves in Fathom and Arrow, with being steady state, they're going to be either open or closed, okay? And so there's a lot of simplified ways that you can model relief valves in our software, and that just, it's nothing to write home about, really. It is what it is. But why would you need our software for it? It's because you want to focus on the piping itself that's connected to your relief valves And you also want to be able to identify how your relief valves are going to impact your overall system performance. If you have relief valves popping open and you've got flow through them, what's that doing to the flows and pressure distributions in the rest of your system? Do you have other issues that are materializing? So right now, I'm going to start stepping you through bit by bit on how you would use Fathom for modeling relief valves in liquid systems, then how you would use Arrow to model relief valves for gas piping systems, and then finally AFT Impulse. That's where the real fun begins with modeling relief valves, because in AFT Impulse, when you're modeling a transient simulation for a waterhammer event, you can see how your relief valves are opening and closing over time, and that can really lead to some interesting behavior that's a lot of fun to analyze. Give me just 1 second here. Hold on. Sorry about that. I had to mute myself for just a quick second. If you've listened to any of my webinars before, you've heard me mention that it's a very dry climate here in Colorado. And if you're ever visiting Colorado, be sure to stop by our office and say hi. But secondly, make sure you drink tons and tons of water. With our dry climate in the high altitude here, then it's very easy to get a really dry throat, especially if you're talking a lot like doing a webinar. So if you all of a sudden hear me drop out for a second, don't panic, just wait a few seconds. It's probably because I've muted myself to rehydrate and avoid the scratchy voice sounding. Okay, let's go ahead and get into this. This is a Fathom model where I have modeled 7 different systems that are all independent of each other. I'm going to break things down one by one because there are several ways that you can model relief valves. As I discussed, when you are dealing with AFT Fathom, it is a steady state tool unless you are using the AFT Fathom XTS module for doing transients. So in that case, your relief valves are either going to be open or closed. So the actual relief valve junctions that are in my model are these 4 systems right here. Those are relief valve junctions that will model a relief valve. Well, there are other ways that you can do it, which are even more simplistic. You can use a regular control valve junction. You can use a regular valve junction or an orifice plate. If you're using the same conditions, these 3 methods will be exactly the same as if you're modeling a relief valve in this fashion. Now, right now, I've got some results in my model. Let me go ahead and clear them out really quick to show you what things would look like. So once you draw your relief valve on the model, you're going to see these pipes that have some dotted lines. Those dotted lines that you have they mean that you have a closed off flow path, and there's initially no flow in that pipeline right there. So your relief valves in the software, when you first draw them, are going to start off closed during your analysis. If your pressure gets to be above the set pressure that you define, then your relief valves will pop open, and at that point you'll see flow through the lines, and they won't be dotted lines anymore. They'll be solid like this when you look at them in the results. So what do we have going on in my system here? What I have done is I've modeled the same system pressure at 200 psia. So that's the supply conditions for each of my systems. What this is simulating is if I have some event which causes the pressure to increase dramatically, this is the supply pressure that's being fed in, which is causing my relief valves to pop open. That's my really high pressure. So in reality, I am modeling a whole piping network right here with a simple assigned pressure junction. I'm fixing the pressure at that boundary. I don't care about what is going on upstream of this. All I care about is the pressure right here, and this is the pipe where the relief valve is connected to the system. that is better well represented in this system right here. So in this particular case, in the upper right-hand corner, I have my piping network, and then let's say that I have a takeoff that leads to somewhere downstream, which happens to be atmospheric pressure. That could be a completely different pressure. It doesn't matter what it is. You could have an actual closed loop system where you've got additional piping in that flow path, and you've modeled a whole bunch of other fittings and junctions. So what this is doing is I've put a branch junction right here. This is where I've connected my relief valve. So this relief leg is the same thing as this leg right here, or this leg, or this leg, or this leg. So all of those are equivalent ways of modeling the same thing. Now, why have I used a control valve in this particular part of the system? The reason why is because maybe you only know what your relief capacity is. In my particular model, what I did was I set things up first. I actually wrote a blog about modeling relief valves a long time ago. You can find that blog on our tips and tricks page, but I'm going in a bit more depth today in the webinar. And so when I was developing that model, I initially was trying to model the relief valve itself, and I calculated what the resulting CV and flow rates were through my system. And so I assigned that exact flow rate right here in my flow control valve. So this is something I back calculated, but if you know what your flow control valve capacity is, you can assign it here. Why would you do this? Well, the way that a control valve junction works is we're going to change the pressure loss across that component until your set point is met. Once the set point is met, we know what the flow rate through that valve is. We know what the pressure loss across the valve is. We can then calculate a CV value. We can also calculate a K factor. We can calculate an equivalent orifice diameter if you want to use an orifice plate with a discharge coefficient of 0.6. And so the relief valve or the control valve junction is really useful. In addition to just modeling a real control valve in your plant, you can also use the control valve to size regular valves, orifice plates, or relief valves. So this is my relief capacity. That's going to calculate what my relief valve CV value needs to be. So when it comes to relief valve sizing, this is as easy as it comes. It's not that difficult. And using our software makes it very simple. And you can do it in different ways. If you don't know what your flow rate is, but you know what your pressure needs to be, either downstream of the relief valve or upstream of the relief valve, you can use either the pressure reducing or pressure sustaining options. And that way, it will calculate what your flow capacity is through the relief valve to ensure a fixed upstream or downstream pressure. Now, let's say that your relief valve set point is not based upon what's going on right at the relief valve itself. Let me collapse this window and show one of the other systems. Let's say that your relief valve right here, the set point that causes that relief valve might actually be based upon the pressure right here. Well, if you have something like that going on, where your relief valve is going to open up based upon a pressure or a flow rate somewhere else in your system, not immediately at the relief valve, that's where our Goalseeking Control module comes into play and is incredibly useful. So if you have a license for the Goalseeking Control module, you can turn it on by clicking on this button right here that's just to the left of the status light. So when I click on that and I turn on Goalseeking Control, what I can do is I can assign goals and variables. So what I might specify is my variable is going to be my relief valve loss value. So this is the loss across relief valve J404. And my goal would be a particular, maybe it's a flow rate in a certain pipe. So if I want to modulate my CV value based upon a certain flow capacity right here, or maybe a pressure, then you can easily do that remote capability with the Goalseeking Control module. So here, I would say my flow rate at, or let's say my pressure. If my pressure gets to be equal to 200 psi at the inlet of P401, then change my CV value for that relief valve. And that can help you find another way to size your relief valve. You can do the same sort of thing by using the Goalseeking Control module for control valves. And that allows you to do some more advanced remote sensing capabilities. So as you can see here, there are so many different ways that you can skin the cat. After I ran my model and I calculated what the CV value was for this control valve, I also calculated the K factor. I assigned that CV directly in this valve right here. Then I calculated a K factor, which was equivalent to that CV, and my K factor is assigned directly for this orifice plate. And then finally, in my relief valve junction itself for the loss model, I assigned the same CV value. So if I assign a CV value of 5, and I use the same CV value for this relief valve, and if that CV matches up appropriately with the K factor for this orifice plate, all of these systems will be completely identical with the flow rate that I see through my control valve. So there's self-consistency between all of those different systems that I've modeled there. Now, let's talk about the relief valve itself. There are 3 different ways that you can model relief valves, and these pictures will help you understand which type of situation you would be needing to use based upon how you've modeled your system. I'm going to focus on the internal relief valve option first. So if you select internal relief valve, what this means is that your relief valve is in line with piping, and when you have your relief valve pop open, it's going to relieve into additional piping. So that is my bottom case right down here. So here's my system, the big box, the big giant piping network, and the only thing that I care about is the fact that I have a really high pressure at the location where my relief line connects into it. So when that pressure is higher than the set pressure for my relief valve, this relief valve is going to pop open and I'm relieving into additional piping. So my relief valve leads to pipe 302, which eventually discharges into the atmosphere. It doesn't have to go into the atmosphere. It's just doing that in my particular model. This could be discharging into a tank. This can be recycled back to another portion of your system. It can be sent to another overall relief header in your whole network. It can be whatever you want. The only thing that I've done is I've simplified it, and I'm relieving to atmospheric pressure after the flow has discharged through some piping right there. So that's where I'm using the internal relief valve option for this particular system. The next thing that you would specify is what your set points for your relief valve is based upon, either your head or your pressure. And if you assign pressure like how I've done, then you have this option here to model a constant back pressure relief valve. That would be a balanced relief valve that has some sort of bellows device on it. And the unique thing about that is you can specify what your set pressure is directly. So here I've got my set pressure at 50 psia. If the pressure at the relief valve is higher than that value, that will cause the relief valve to open. And in steady state, by default, we're doing an instant opening or instant closing. Well, that doesn't mean very much for steady state, because again, your relief valve is either going to be open or it's going to be closed. That's really all there is to it. There's not much more than that. Now, the reason why instant is useful is because of the loss model here. So if I have a loss model where my relief valve is either going to be open or closed, I can go into my loss model tab and I have any of these loss model options. You can do a CV value, you can do a K factor, a resistance curve, or a new feature for Fathom 10 is you can do the CDA constant. This is where we have now built in your relief valve API designation for API code 526. So if you're dealing with the API relief valve, then you can use this to model relief valves a little bit more closer to what they actually are. So when I use an instant opening and an instant closing, it's just a single loss value and that's it. If I switch to using pressure, there are some more pieces of information you need to specify. I have a pretty little graph here that illustrates what's going on. The green line right here, that is when my pressure in the system exceeds my relief pressure. So that's my cracking pressure right there when my relief valve barely starts to open a little bit. The next thing that you need to specify is your overpressure. The overpressure is the pressure at which your relief valve is fully open. So if my relief valve is fully open, once the pressure gets to be 60 psia, this is what's going to dictate how open your relief valve is. So it's not just going to be fully open or fully closed in this case. Your relief valve will be somewhat open depending on what your system pressure is. And so this curve is dictated based upon your set points as well as your loss model. So now if I go back to the loss model tab again, you can see that I have a new option that's available for me, linear based upon set points or nonlinear. So what I'm specifying here is my fully open CV value. My fully open CV, maybe it's 1,000. Well, in that case, based upon my fully open CV, that's going to be my fully open CV value at this pressure, and then whatever the system pressure is at the relief valve, that's going to dictate what my overall CV is and how open my relief valve would be. You can do your CV curve either linearly or non-linearly, so you can get really fancy with all that. In my particular relief valve, I'm just keeping things simple. I'm doing just a single open or closed relief valve, and my fully open CV is going to be a CV value of 5. I just picked that number out of the air when I wrote my blog a long time ago. The blowdown pressure is the pressure at which the relief valve closes. So it is possible where they can be the same. That way, the relief valve will open and close at the same pressure. But if you want to make that blowdown pressure lower, you certainly can. That way, your relief valve won't close until the pressure drops even further than the set pressure. And so that can offer further protection to your system. So this is one way of modeling the actual relief valve junction. I am calling this a case 4 internal relief valve with vent piping. And then this system here, I'm calling it case 4A. The reason why is because I'm modeling the relief valve in the same exact way. Let me move my quick access panel here. So this relief valve is modeled in the same exact fashion as this one right here. I'm using the internal relief valve option. The reason why is because when this relief valve pops open, it's going to relieve into additional piping right here. It's not just going directly into the atmosphere with no piping downstream of my relief valve. So this is exactly the same as this right here. Now, why am I doing it this way? I'm doing it this way because I want to capture a little bit more of the effects of what's going on in the system here. So really the equivalent point is my branch junction and my assigned pressure junction. Those are essentially simulating the same thing, okay? So I have 200 psia right here, and then I'm asserting that I would have 200 psia right here as well for my relief valve to pop open. Now the thing is, the pressure would not actually be 200 at this branch junction right there. My 200 psia is assigned at the assigned pressure, and this pipe right here is 50 feet long. And so there is a little bit of pressure loss in that pipe, so my system pressure will be slightly below 200 psia. However, that pressure is still going to be higher than the set point of my relief valve, which is about 50 psia. So because the pressure in this line is higher than the set point, this relief valve is going to crack open in the same fashion that this relief valve will, and there will be flow to the downstream piping. So that's what we mean by using an internal relief valve. You're relieving into additional piping. Here's another way of modeling a relief valve where you are actually discharging into atmospheric conditions. So there's no downstream pipe in that case. So if my pressure at the relief valve, which the pressure in this pipe initially is going to be the same because there's no flow. So the pressure here at the branch is going to be the same pressure at the relief valve. If that value is higher than the set pressure, this relief valve pops open and I've got flow into the ambient conditions. So let's open up that relief valve and see what we have to specify. What I've done is I've used the exit option. So when you use the exit option, this picture hopefully clearly shows that you're discharging into ambient conditions. When you do that, the next piece of information that you have to specify is your pressure of the ambient conditions that you're discharging into. That's what this exit pressure term means. So that is simply your ambient pressure, okay? If you're discharging into atmospheric, it's atmospheric pressure. If your relief valve is discharging right into the bottom of a lake, well, then it's going to be your surface pressure on the lake plus your rho GH term. So that's how that exit pressure is going to be defined accordingly. And then I'm using the same constant back pressure relief option. So my set pressure is exactly 50 psia. My loss model that I have defined is the same as it is before, a CV value of 5. And that, when it pops open, is going to discharge into the ambient conditions. Now, there's another way to model a relief valve that's discharging into atmospheric conditions. That's this option right here. This is called an inline exit. Why do we call it an inline exit? The reason why is because you have piping right here, and your valve is connected to two pipes, upstream and downstream. But notice that this system is not the same as this system. The reason why is in the system on the left, there's no flow through it initially. For the system on the right, over here, there is flow. I'm actually flowing through that relief valve to this atmospheric condition through that pipe 602. So there is flow through that initial path right there. So what's going on is when I use the inline exit option, it's a convenience tool, okay? What this allows you to do is it allows you to model flow through your path as well as flow into the ambient conditions with a single junction. Why would you do this? It allows you to ignore having to model that extra pipe right here, and you don't have to model the branch. You can simply connect your relief valve immediately to the piping. And so this is just a simplified method or a simplified version of modeling this system right here. So it's a convenience option. It's modeled in the same way. My relief valve is exiting into atmospheric pressure, not a downstream pipe. Those downstream conditions are at 14.7 psia, and my set pressure is exactly the same as it was before, 50 psia. And then my loss model is a CV value of 5. So as you can see, there are several different ways that you can model relief valves in Fathom. And again, when you're using a flow analysis tool, it's not just about the relief valve itself. The reason why you're using a flow analysis tool is because you want to see the effect of your relief valve on the rest of the system with what's going on. So I'm going to go ahead and run this model now. And if we take a look at the output, we don't have any warning messages, but what this does tell us is that I have several relief valves that are opening up. That's good. All this is doing is it's telling me that each of my relief valves are opening because I have a pressure that's higher than the set pressure. Now let's take a step aside really quick and see what's going on here. I'm going to dock my output to the right side of the window, and we're going to look at the first relief valve J302. That's this guy right here. Remember, this one is the internal relief valve where I'm discharging into additional piping. Initially, there is no flow in that path. So because my flow rate is exactly 200 psi here, and there's no flow through it, the pressure at the relief valve will be exactly 200 psi. That's what this message is telling me, and that's why it's telling me that my relief valve is popping open. So my relief valve is clearly above the set point, which is 50 psia. That relief valve is popping open, and I am relieving to the additional piping right here. And as you can see, you now have solid lines, not dotted. That's because the relief valve has popped open. Now let's take a look at the next one here. If we take a look at J602, that's popping open because when the relief valve is closed, the pressure is 107 psia. Well, what's going on with that? If you remember, in this particular system here, there was, well, these are appearing to be out of order. Let's look at J404. That's the one I want to focus on. I don't know why these are out of order here. They should be numerical in my mind. But anyway, junction 404, if this is modeling the same path as it was on the left, why is it that the pressure is different? It's 163 psi, not 200. Well, the reason why is because I have flow through this line. This relief path was initially closed. So when this flow is going through my pipeline here, the pressure at this point is actually 163 psi. So I've lost about 38 pounds of pressure in this upstream pipe by the time it gets to the point where my relief line connects. However, this value is still higher than the set point, so that's cracking open. And then if we take a look at junction 504 and 602, you can see what their conditions are. The pressure here is 115 or 115.8 psia. Again, that's because you've got flow through the system. And then in the last junction, J602, you've got flow through the line, but no connector pipe right here. Now, on my visual report, you can see a little bit more about the piping details. So here, I've modeled this system exactly the same. All of these pipes are 2 inches in diameter, and the pipes are all 60 feet long. And so what you can see here is I've specified a flow through that relief valve of 67 gallons per minute. In this particular valve, I directly assign the K factor. Same thing here. And then this is using the CV value for the relief valve. As you can see, the relief flow rates are exactly the same. So this just goes to show that when you want to model relief valves in the software, you do not have to only model the relief valve junction. You can still do it in several different ways, which could be a lot easier, especially if you're trying to size your relief valve and see how it impacts the software. So those systems are all consistent and we can see what's going on. Now, this particular flow path right here, I've got the same flow path almost, but I only have 50 feet instead of 60 feet. So I've got 50 feet and then 10 feet. That's my 60 feet to the relief valve. But there's a pressure drop because I've got flow through that path. That's why these results here for this system are slightly different, because this is not completely identical to this. It's just a different way of modeling things. Now, if I would boost up this pressure and change it until the pressure here is 200 psi, then it would be exactly the same. So that's just a step that I didn't do. And you can see here that the flow rate is 58 gallons per minute. And then you can see how this system, it's discharging straight into the atmosphere. What's going on here? Well, I have 60 feet of piping downstream of this relief valve that is contributing to pressure loss before the flow gets into the atmosphere. In this particular relief valve, I'm discharging straight into the atmosphere, so my pressure at the outlet of this pipe is 107 psia, and then it's discharging right into 14.7 psia. So there's a higher pressure loss across that relief valve potentially that you might see. That's why your flow is going to be different than what you see here. Now, if you look very carefully, you can see that there's two flow parameters that I've added for each of these systems here. For junctions, there is a value called volumetric flow rate through junction and volumetric flow rate net at junction. Well, if you look at the volumetric flow rate through the junction, that is flow that is through the junction. But in this system here, what do we mean by the word through? Well, the answer is it's ambiguous. A, you have flow through the relief valve into that path, and then you have flow through the relief valve into the atmosphere. So does this through represent either of these or combination of them? It's ambiguous. So that's where you have to find another parameter. So if you were to open up your output control window, which is right here, this is where you dictate which parameters you want to display. I have gone to the junctions button and I scrolled down in this list, and this is the volumetric flow rate net at junction. And so as you can see, that volumetric flow rate net at junction, which is in my visual report, which is right here, that's my actual relief flow into the atmosphere versus the flow that's leading into the downstream pipe. So hopefully this gives you some ideas and some inspiration on how it's really easy to model relief valves in your piping system. Give me just 1 second here. Okay, so that's all there is to it. You can model the relief valves in different ways, but again, it's all about the piping. Let me show you something else really quick before I move on to Arrow. So if I go to open up another relief valve model that I want to demonstrate here, I've got a piping network. This model is from one of the previous webinars that I did demonstrating the Fathom ANS module, where I essentially sized this entire piping system in order to minimize the overall piping weight because I did not have actual cost information. So it was a simplified sizing process. Well, initially in that system, I did not have these relief valve flow paths. I added those in for today's webinar. So I started messing around with this system to make it a little bit more exciting. And I'm simulating an event where, let's say that somebody ramps the speed up for each of these pumps to like 115% speed. So if they're operating really, really fast, that's going to increase the pressure in my system, because on your pump curve, you've got your pump curve. And then when you have the affinity laws, if you have a higher speed, that's going to shift your pump curve out and higher. So that's where you'll have a higher pressure. So I did that because I wanted a higher pressure in the system. And then I actually did a system where I'm pretending that these relief or these control valves here are failing open. So when they fail open, these heat exchangers are going to see the full system pressure, which could be really high. So if those are pressure sensitive, I don't want the high pressures to see those relief valves. So that's where I put in a relief line upstream each of those heat exchangers. And so initially these two relief valves are closed. If the pressure in the system is higher than the set point, those relief valves will pop open, and that flow will then come back down into the tank there. So that's what I'm doing with this particular system. So for each of these relief valves, they are slightly different. I'm only going to show you one of them. This particular relief valve here, I was just making up numbers, okay? So don't beat me up when you see that this is not sized properly. It's made to show you a relief valve problem that you might run into. So I just made up numbers. I made up a set point. Now I'm doing a remote sensing. This is real useful because this relief valve is not connected immediately to that heat exchanger, as you can see. Well, if I still want that relief valve to pop open based upon a certain pressure at the relief valve, that's where you can do the remote sensing. So I want this relief valve set point to crack open when the pressure is 52 psig at the outlet of pipe 37. That's right here at this heat exchanger. If that pops open, my overpressure where my relief valve is fully open is 60 psig, and then when my relief valve is fully closed, it's at 40 psig. It's an internal relief valve, so I'm relieving into additional piping. And then lastly, I am modeling a set point where when I use that option for the pressure, my fully open CV is 300. So that's how I've modeled that particular relief valve. The other relief valve in the system here is similar, but there are some slightly different values. And I'm not going to show you the input for that for the sake of time. So this is why you got to do a flow analysis, because you can't just size your relief valve and call it good. You want to make sure it actually works when you put it in your real system. So let's say that I went and I sized my relief valve, but I wasn't really doing a thorough analysis of what's going on in the overall system network. Here's something that you might run into, which is a bad thing that is happening. And it should converge here in just another second or two. There we go. Okay, so we've got some warning messages. This is telling me that my relief valves are opening because the pressure is higher than the set pressure. So my pressures right here at those heat exchangers are higher than the set points. Therefore, the relief valves pop open. But then you see the other warning messages down below where a unique solution is not possible, relief valve cycles. What does this mean? Well, what this means is initially, if I zoom in a little bit here, initially this relief valve is closed and there's only flow through that path. Well, when this relief valve is closed, the pressure here at the heat exchanger was higher than the set point that I defined in the relief valve. That caused my relief valve to pop open. Once that relief valve pops open, I now have flow through two paths. This path here is still getting a little bit of flow, and now I have flow through this path. When there's flow through your relief valve, it's trying to reduce pressure. Well, the thing about this particular relief valve is it reduces the pressure so well at the heat exchanger by removing some of that flow that your pressure at the heat exchanger drops below your set point. Well, when you have flow through this path and through your relief valve such that your pressure drops below the set point, your relief valve closes again. Well, when your relief valve closes, the pressure right here goes back up, causes your relief valve to open again. And when that relief valve is open, you've got flow, and then the pressure here drops, and so the relief valve closes. That is cycling behavior where there is no steady state solution for steady state analysis. That's exactly what these two warning messages are telling you for those two relief valves. So if I was to go to the relief valve summary tab right here, I would see that there is no solution. So these results are basically invalid, because in reality what would happen is your relief valve would be chattering massively, and that's definitely a problem that you want to make sure that you avoid. So this is why I wanted to show you this particular model, is because when you're sizing your relief valve, you don't want to just size it and call it good. Make sure that you actually model the relief valve in your system, and then model your upset condition directly where you have higher pressures. That way you can make sure that your relief valves will actually perform just like they're supposed to. That way you avoid chattering behavior. All right, so that's what I wanted to talk about with AFT Fathom. Let's talk about a nuance with relief valves in terms of AFT Arrow. A while back, I had a technical support case come in where they were asking for my advice on how to model the relief path right here. So what they had is a steam drum where the conditions of the upset is a relief part right here where they have pressure at 566.5 psig, and the temperature is 482.8 degrees Fahrenheit. So they're asking for guidance on how to model this relief path right here. Well, I took that screenshot and I started building a model of their system. So here's my AFT Arrow model, and I've done it in 3 different ways because initially I didn't know what the, you may not know what the actual conditions are for your relief valve. So we know what the relief capacity was. He told me, so I used my flow control valve first because I wanted to determine what the relief valve CV value should be. So I built my system, but before I ran my model, I did a quick check. He told me that I've got steam in the drum and it's at saturated conditions. Well, that's not good. That's not something that AFT Arrow models, is saturated steam. I opened up our steam calc utility and I plugged in 56.6 psig, 482.8 degrees Fahrenheit. As you can see, that's a liquid. You're going to need to use AFT Fathom for that if that's your condition at your supply. So using AFT Arrow would not be the proper tool. However, we know that the fluid is very easily going to vaporize, or it could easily vaporize. So what I did was, if I was to try and model my system where I've modeled my supply, if it was initially at 482.8 degrees Fahrenheit, like the original conditions, this system would have a lot of difficulty solving. You'd get a whole bunch of warning messages. That's because you would see condensation in your piping. So what I did was, in this particular scenario, I simply bumped up the temperature just a little bit. That way, if I get any condensation in the piping, Arrow will tell me, but at least my supply pressure and temperature is slightly above saturation. So that way, at least I have a better starting point where Arrow can tell me what the actual composition and flow and velocity and all that stuff is. So I already ran the system here where I've got results. I modeled my flow capacity directly in pounds per hour. And then in this orifice plate, he told me what the orifice area was. He told me the discharge coefficient. And then I calculated a CDA value because I want to know if there's sonic choking across that orifice plate. That's another nuance to you making sure that you use Arrow for modeling your relief valves for gas and steam systems, is to identify if you have sonic choking. And then finally, my relief valve here is an internal relief valve, just like I showed you in Fathom. And then the loss model here is based upon a CDA value. because I know what my orifice area is and my discharge coefficient, and there's my CDA value to determine what my choked mass flow rate would be if there is sonic choking. So after I ran this model based upon 483 degrees, I got a whole bunch of warning messages. And it looks like this wiped out some of the results. Let me rerun it again here. I actually do have a slide of the warning messages that you would see. So what you would see here is with this system where I'm using 483 degrees Fahrenheit, I have all these warning messages telling me that the actual temperatures are below my saturation temperatures at all of these piping stations. This means that you have saturation in your piping. Okay, there's condensation going on, two-phase flow behavior. The results that Arrow is predicting are going to be unreliable when you have that two-phase flow behavior. That's one problem. The other problem is because we have that two-phase behavior where the steam is saturated, if we don't know what the quality of the steam is, we can't calculate all the thermophysical properties. So that's where we have these convergence issues right here. So because we have saturation and convergence issues, you've got some major problems in that piping, and Arrow is not going to be able to necessarily know for sure if the results will be correct. So that's where I had to do another scenario where I bumped up my temperature. So in the next scenario that you'll see here in a second, I increased the temperature of the supply to 518 degrees Fahrenheit. That was an iterative process. I slowly bumped up the temperature to figure out what the minimum temperature supply needed to be in order to eliminate all of the condensation. This shouldn't take too much longer to run. Let's see, I did get a question that came in. Can you enter KB valves for derating due to back pressure? I honestly don't know what a KB curve is for derating. So if you could send us some more information on that, we can look into it for you. But as far as I'm concerned, I don't know of any areas where you would assign a KB value, but that's a question on the spot that I don't know the immediate answer to, and would have to look further into your question. Let's see here. So this is the results here based upon the supply temperature of 518 degrees Fahrenheit. So what we see here is the flow rate is fixed through my control valve piping. That's exactly what I assigned. If I do not specify the flow in the orifice plate or the relief valve, these are the actual flow capacities that I will see, which actually the flow rate in the relief lines are a little bit higher based upon the orifice area of the relief valve and the discharge coefficient that the person gave me. So that relief valve sizing to determine the flow capacity was not completely correct. Additionally, I have sonic choking in the system. This does not mean that the results are bad. AFT Arrow is the best tool for being able to handle sonic choking properly. This is just telling you where it's happening at. Let me see if I've got results now. Okay, so this is the 483 degrees. For some reason, these saturation warning messages were dropping away, and that's what I wanted to show you. So 483 degrees, not going to work. Now, 518 degrees, if I go to my model data window, you can see where I've specified that directly right here. I don't have any bad warning messages that I'm concerned about. What this is telling me is that I do not have any saturation or condensation happening inside the pipes. Keep in mind though, these pipes are adiabatic, meaning that they're perfectly insulated. So with those, if they're not insulated properly, then you will have some higher temperature drops that will cause more condensation. So your actual temperature might need to be higher, or you might need to put some insulation on there. So here's where it's telling me I'm sonically choked. I'm sonically choked at several points. all of the outlets, as well as the orifice and the relief valve. The control valve junctions and arrow will not tell you if you are sonically choked. However, it will tell you if the flow rate is higher than the sonic flow rate, and it won't let you model that. So that way it at least knows if you're modeling above sonic conditions. So what this just means is that I've got pressure waves across those components which are due to sonic choking, where the gas has really reached the speed of sound. And this is my 518 degrees. Now, my last scenario that I wanted to do was I wanted to tighten up the flow rates a little bit more. And so I used the Goalseeking Control module for that. As you can see, I specified variables for the orifice and relief valve CDA values. And then my goals were to achieve the same flow rate that I got in the previous system here, where I'm fixing the flow rate directly. So this is where you might need to use the GSE module to tune your relief valves to what you're actually expecting to see. So if I was to do that analysis, I would calculate that the actual, let me pull up the slide here. Based upon my relief valve CDA that the user told me of 14.05 square inches, my flow rate was about 3% higher. If I use the GSC module to adjust my CDA value down to 13.7, I'm then within 0.11% of my relief flow rate. So that way I was able to get my relief valve tuned a little bit closer to the actual flow capacity that I want to see. So when you're dealing with AFT Arrow, it's a lot more complicated. There's compressible flow effects that you have to pay attention to. Also, you have to see if you're condensing, and that can cause some other issues. So that's relief valve modeling in AFT Arrow. Last thing, AFT Impulse. In AFT Impulse, I have a situation where I'm modeling a transient analysis. In the transient analysis here, the main thing that's going on is I'm modeling a pump trip. Okay, at some point in time, I have a power failure and the pump all of a sudden trips and it's not supplying pressure anymore to my system. In addition to the pump trip, I have a isolation valve failure where for some reason something causes my valves to close a lot faster than what they're supposed to close at. So those two valves, if I open it up, it's closing in 2 seconds. That's a very, very fast closure. That's a lot faster than it's supposed to close. So what I'm needing to do is determine what my maximum pressure is in the system, and then to determine if I need to put a relief valve. So my system above has no relief valve, system below has the relief valve. I've defined a design alert where my maximum pressure in the system cannot exceed 400 psia. So if the pressure at any particular time step is above 400 psia, the warning messages in Impulse will yell at me about that and identify where it's happening. So it's a good way to check if you're maintaining code compliance. My relief valve here is going to be modeled as a passive relief valve. In AFT Impulse, you have some more flexibility and more options. This is why I said that Impulse is a lot more fun with modeling relief valves, because you can see how your relief valve chatters and responds during a system transient. Excuse me. So I've selected pressure as my opening and closing profiles. So these are my set points. And then based upon those set points and my fully open CV value of 4,200, this is going to dictate how my relief valve opens and closes over time. Now, one thing that's really useful with relief valves in AFT Impulse is rate limits. If you know that it's mathematically, Impulse will calculate whatever CV is required in order to maintain your set point. And so you might see a situation where, based upon how the pressure is changing at the relief valve, it could cause your relief valve to mathematically respond way too fast, faster than your relief valve can respond in reality. So when you specify rate limits on the loss model tab, this is where you can say, hey, don't let my relief valve open or close faster than this particular profile. And that way it'll respond more realistically. So that's what's going on in my system. I've already specified a couple of groups. I've got a path to the relief line. I've got a path with the relief valve, a path without the relief valve. That way I can do graphs. Now, there's something I want to point out about how there's an issue with the person that modeled this system previously. I want to see if you can figure it out before I can get there by looking at it. So I've already ran the model and I have some results, and we see that we've got some design alerts. In my system that does not have the relief line, that's where my design alerts are yelling at me that the pressure is higher than my maximum allowable pressure. That's a problem. Well, how are things actually changing over time? Let's take a look at the animation of pressure in both of those two flow paths. I've already created that as a graph list item. That way I didn't have to reset the parameters. So what I'm showing here is the pressure as well as the flow rate along the flow path in the main header line. The red line is without the relief valve. The blue line is with the relief valve. And then with these labels, I've identified where all the different junctions are. So let's play the animation and see what's going on. My pump is tripped and my system pressure is dropping. My isolation valve is closing. And when my isolation valve closes, you can see how the pressure is going to increase at the discharge of the system very quickly here. So give it just another minute or another second. Okay, so now you can see how the pressure is dramatically increasing. Look at this. The red line is much higher than the blue line because my pressure has exceeded the set point. So the blue line is now going to have flow through the relief line. That's why this pressure is not so high. So as you can see by looking at this animation, Impulse or the relief valve is doing a good job at relieving my flow and keeping my pressures below that 400 psia maximum, which as you can see, that 400 psi maximum is sustained at a lot of areas in your system as well as over long periods of time. So that's a real problem that's going on. Now, that's what's happening in the overall main line. Let's take a look at what's going on with the relief valve. If I right click on the relief valve, I can generate a transient graph. Here's how my relief valve opens and closes. So if I zoom in on the x-axis down here, my relief valve is initially closed for a period of time, and then once it sees that high pressure, it pops open. Now, what you see a little bit later is a blip where it opens up a little bit more and then it comes back down. Well, when you saw those pressure waves oscillating back and forth, there is some sort of interference that caused a little bit higher of a pressure, and that higher pressure caused the relief valve to open up a little bit more and then drop back down. So that's what the relief valve CV profile looks like. This is why modeling relief valves in Impulse is a lot more fun, because you can see what's going on over time, and it's not just going to be a single value. You can see how it changes during the transient. This is how the flow rate through the relief valve changes. So my relief valve pops open. This is how the flow rate through the relief valve is actually changing during a transient. So it's just a very simple graph that you can generate on the fly. Now, let's talk really quick about how the system is modeled, which is not an appropriate way of modeling the system. Why is it that this system seems to dampen out so quickly and stay at such a high pressure? Well, the reason is because I have used these magical assigned pressure junctions that will specify a fixed pressure at that location. This is not an appropriate use of the magical boundary conditions that will specify pressure or flow. So what's happening here is even when my pump trips and my valve closes, this pump speed is going to come down and it's going to decay. But if I was to plot what the pump speed decay is, you could see how this pump never actually spins down to zero. So something is causing this pump impeller to still spin at 20% speed. Well, what's going on? It's because I am imposing a fixed pressure of 200 psi at all time steps. This is a reflecting point of a constant, of a constant pressure. So when you're dealing with impulse, do not do this, because in reality, you've probably got system upstream of that where you do not actually have a fixed pressure that's a reflecting point. Your pressure is actually going to change and pass down to the system upstream. Now, if you happen to know, let's say that you had a pressure transducer that was telling you how your pressure at that point changed over time, and you do not want to model the rest of the system upstream, well, what you could do to be an appropriate usage would be to go to the transient tab, and this is where you can model your pressure change versus time. So this is where you would plug in your pressure versus time data. That would be a more appropriate use of the assigned pressure junction in that case, but not here, not like this, where it assigns a 200 psi. So that's why we still have a significant amount of flow even when this valve is closed, is because I'm pushing all this flow constantly at 200 psi through the system. That's why it dampens out so quickly. All right, everybody, thank you very much for your time. That is how you can model relief valves in different ways in AFT Fathom, AFT Impulse, and AFT Arrow. If you have any other questions, don't hesitate to send us an email or give us a call. Our contact information is on our website. Thank you very much and have a wonderful rest of your week, everyone.